Merhabalar. So this is a new chapter. Name of this chapter is two-port circuits. This is the highest level analysis method that we will be using within this course. That's why it is important. So we are going to introduce what two ports are, why we need them, and then how we can represent these two-port systems, so how to calculate these two-port systems parameters, and then the third frame is two-port circuit analysis, how we are going to represent or describe or find the equivalent circuit of two ports, that is, or the model two-port circuits, and then how we are going to use this model for the analysis, and then if we connect more than two ports together, what would be the equivalent two-port circuit parameters is the last subject that we will be examining. Let's go into this first one now. So we've got to define port definition first. If there are two terminals, we say these two terminals make a port if one of the terminals incoming current is equal the other port's outgoing coming. Then these two terminals are called a port, or these two terminals make a port. So in practice what I am saying is this. Consider two terminals. One of the terminal, a current go into that terminal, and there is another terminal of which current coming out of the terminal. If those two terminal currents are equal to each other, then these two terminals are called port. You might consider that all the elements could be a port, but there are some exceptions. I will explain it later on. So why we are trying to define these two ports? So the analysis we have done up to now, one of them is the classical method. You're going to write two any equations and solve two any unknowns. You can solve that, find out all the elements, current and voltages. And then we said we could reduce the number of equations that we are going to write by using the mesh current node voltage method. Once again, these analysis methods are also used for the analysis of all the elements. That means all the elements, currents and voltages is going to be found. Are going to be found. Serial parallel connections, how we use these connections, or equivalent impedances usage in the analysis has been examined. Source transformation, once again, is used in the analysis, and that has been examined. And Thevenin-Norton equivalent circuits, how we use these equivalent circuits for the analysis. So this Thevenin-Norton equivalent circuit analysis, we said if we are dealing with only one of the element, current and voltage, so Thevenin-Norton equivalent circuit is useful tool for us to use. Now the last question coming in is this: could it be possible to model a circuit according to its input and output, under the condition that excluding the input and load elements? How this could be used in practice? So make it more clearer. Assume that you have circuit. Each electronic circuit has an input and an output. So we are saying now, if we remove that input and remove the output, there is a circuit left behind. So the question now, can I represent this left behind circuit somehow? If I do so, that representation might be called equivalent circuit, it might be called a model, it could be a two-port system, it could be called a two-port system. So if I do that representation, then I end up with saying that whichever independent source you use, whichever load you connect to the output port, I could find out the input variables and also the output variables. That means input port voltage and current, output element voltage and current. I can calculate this voltage and current. So that means we are not calculating all the elements current and voltages, but load voltage and current and the input voltage and current we can calculate. So that is the main core part of this subject. So the next thing we're going to see how we can model this circuit. So in order to see that, we've got to move to open board. Let me move to this open board and clear that area. In here, you see this is the input port and that's the output port. Why we said this is input, that's the output port? As you see here, we are saying these two terminals, one of the current for this terminal going in, for this terminal the current coming out of terminal, they are equal. If they are equal, then this is input port. So this is output port. This incoming, for this terminal, this incoming current is equal to this outgoing current here. If they are equal, then those two make an output port. So you might say that all these elements, all two terminal elements have got that property. So all two terminal elements are considered as ports. But what about the four terminal elements? For this one, for example, that's not easy to say. A transformer like that and say this is port A and this is port B, and this current is equal to this current, isn't it? Same line, and this current is equal to this current, no problem. So what about this current A, this current IA prime, that current IB, and current this IB prime? So I know that IA equal IA prime and IB is equal IB prime. So A and B, A is a port and B terminal B terminals are port. But what about A and B here? That's A prime. So what about A and B? Is this equal? No. You cannot say that, isn't it? If you use the Kirchhoff, there's no Kirchhoff current law that you can write which includes these two elements, and there is one note for that. And A and B prime, you cannot say this, and A prime, B prime, and A prime, B prime, AB, and A, B prime. for example, this current is not equal to this one. So this is not true. That means these two A and B terminal is not a port, not port, not port, not port, not port. So that's an example. So in some cases, any two terminals within a circuit, you cannot say that these two terminals make a port. That is a counterexample for you. Now the next step now, if there is one port, if there are two terminals, one port element, like that resistor, definition relation, behavior of this port is this, isn't it? What does this mean? If you apply independent current source, that is the voltage that you're going to get from this resistor. Or if you apply a independent voltage source, you can find out the current passing through here by this relation, isn't it? So that means you can write the definition relation in two different forms, depending on which input you're going to choose and which output you're going to observe. So this is the similar thing here. And there is two ports. You can use one port as an input, the other port as an output. So our aim is, what is the relation, input-output relation of those two ports? Since it is just one port, two representation. In here it is two ports. The input-output relations can be written in 6 different ways. That is one of it. We are saying input-output relation. So at the input port of this element, we've got two variables, V1 and I1. In the other output port, we've got two electrical quantities. One of them is voltage, the other one is current, V2, I2. So what is the relation? This V1, I1 and V2, I2 relation could be written like this. If you write it like this, let me write it in matrix form, V1, V2, Z11, Z12, Z21, Z22, I1, I2. So in here, V1, I1, let me make it different color. That V1 and I1 is related with this input port, isn't it? And if I use a different color, this I2 and V2 is related, the second line here, this two. So this is output port and the other one is the input port. So these are the input-output ports voltage current relations. So once you wrote a behavior like that, the relation input-output relation like that, then you can say that you could write the same relation in this format as well. So in here, that was the alternative. In here, there is another alternative for us. So let me write it in the matrix form, I1, I2 is equal Y11, Y12, Y21, Y22, V1, V2. So these two input variables and these two output port variables. So that's the relation between two, but this dimension of this coefficient is the admittance, isn't it? So this is admittance, Y parameters called admittance parameters, and in here impedance parameters or Z parameters. So is there any other alternatives? Yes, there are. For example, if we choose one port current and voltage on the left hand side and the other port current and voltage on the right hand side, this is the relation between the input-output ports, and you can write it another way around. Left hand side, second port, output port current and voltage, and the right hand side, input port current and voltage. So this, if you write it in this format, it is called transmission parameters. If you mix the left hand side, right hand side port variables, that means one variable from the first port, the other variable from the second port, and the other variables on the right hand side, that becomes hybrid parameters. Alternative to this is this. Now what we are saying here, to represent a two-port system, we've got 6 different definition relations, or 6 different equivalence circuits, or represent this two-port system. So if we know these parameters, Z parameters, or Y parameters, or transmission parameters A and B, or the hybrid parameters H and G, then we know the behavior of this circuit. So the next question is going to be, how are we going to calculate these parameters? That is the next step that we are going to examine. But before go to that next step, let's see. Well, let's compare the Thevenin equivalent transfer function and the two-port representation. Let's compare those. So the first comparison, let's make the comparison between the Thevenin equivalent circuit and the this two-port system circuit. So let me throw it here in the Thevenin equivalent. Okay, so move it that way. Thevenin equivalent circuit was this, if you remember. ZS VTH. We said there is a load here, Z load. We said this circuit, apart from load here, in the original circuit, all the elements in here replaced with that Thevenin equivalent, then we can find out this element current and voltage. That was in Thevenin equivalent circuit usage in circuit analysis. In here, compare those two, we are saying in the Thevenin equivalent circuit that input port or input element, independent source, is included in Thevenin equivalent circuit. But in this model, the input is not included, input taken out of the circuit. So what is left is this. That's the difference between Thevenin equivalent circuit and the two-port circuit. What about the transfer function that we have seen? We said transfer function V out over Vi is equal to Hs. So in here, we've got to choose the output terminals and output element. So output element is included while you are calculating this transfer function. Output element is included in the circuit. In here, output element, Thevenin equivalent output element is not included. In here is also not included. And Vi is excluded, isn't it? In the transfer function, Vi is excluded. So that means for different Vi's, I can calculate the load, voltage and current. In this one, this is excluded and this is excluded. Both the input source and the loads are excluded. So that's the difference between this two-port system and the transfer function and the Thevenin equivalence circuit. So there is a list here, single equation as a ratio of two variables. It is just the format type. Two equations, four parameters, two ports. Input element is known if a different circuit is selected. As a output element is known. In the transfer function, output element is known. In the two-port system, output element is not known, so this is excluded. If a different circuit is selected as a load element, then the transfer function changes. In here, if a different circuit element is selected as load element, then the two-port circuit definition relation does not change because it has been excluded. For different inputs, output can be calculated by transfer function. So this inputs for different inputs. For different inputs, if you change the input, output can be calculated by the transfer function. What we are saying, once you calculate the transfer function, for different inputs, you can calculate the output. In here, for different input and output element, definition relation does not change. So if you change this one, if you change this one, your parameter is not changing, then you can calculate this load element current and voltages and this input element current and voltages. So that is the end of this first video for this chapter.